Hello students, in our last lecture we discussed up to the case number 2, and here base of object inaccessible and instrument station in a vertical plane as the elevated object. So here there are main two cases. So in our last lecture we discussed about the instrument axis at a same level. Now today we discuss about the instrument axis at a different level. So let's we start topic. So when the instrument axis at a different level, so in the field it is difficult to keep the height of the instrument at the same level. So here in a some time area is not a perfectly leveled. Okay, so at that time all the instrument are not set up at the same level, so because of the uneven surface of the earth, and at that time this methodology is used to find out the different level and height and measurement. So here the instrument is set up at a different station, and height of the instrument means hi, axis of both the in case taken by the backside on a benchmark. So this line we exactly seen from the figure. So here at the backside both the instrument axis, this one dotted line shown by the dotted line, so both the dotted line intersect at a staff, and we measure the reading at a backside on a benchmark. And there are the two cases is there. So first case is their height of the instrument axis near the object is lower, and second case is their height of the instrument axis near the object is higher. So in this case one by one we discuss on it. So we start with our first case. So here height of the instrument axis near the object is lower, so this one is a object, and uh, nearer object instrument is at a lower part, means this one is the upper part, means at a higher area, and at a lower area instrument setup at a first point at a lower area. And in a case number 2 look like this. First instrument station at a higher position and the second instrument station at a lower position. So let's we start with the first step. So height of the instrument axis near the object is at a lower station. So here we take a triangle. Here this one is object, and top of the object point is a P point. So we take a triangle P A dash and P dash. So we take this triangle, clear? So this triangle here for the instrument 1 we take a h1. So from the horizontal line of sight or instrument axis to top of the point is a h1. H1 is the uh, height of the horizontal line of sight to top of the point, and horizontal distance between the station to object is a capital D. Now we apply the triangulation formulas. So in a triangulation formula, tan alpha 1 is equal to h by d. So here alpha 1, so for the instrument station 1 we take a value 1 1, like alpha 1 h1, then after d1 whatever. So we take a tan alpha 1, tan alpha 1 is a h1 divided by d. Now h1 we take h1 is equal to d tan alpha 1. So this one is a equation number 1 or a formula number 1 for the this case. And now we take another triangle. So top of the point P B dash and P double dash. So we take this triangle P B dash and P double dash. Now then after we apply the triangulation rule for instrument station 2, means alpha 2 tan alpha 2 is h2 divided by b plus d. So here summation for all the lines is a b plus d. So tan alpha 2 is equal to h2 divided by b plus d. Now h2 is equal to b plus d tan alpha 2. So this one is the equation number 2. Now h2 minus h1. h2 minus h1 you exactly seen in a figure h2. So this one is a h2 horizontal dotted line, so the h2 line, and h1 is a lower line, so the h1. So h2 minus h1 is a hd. hd means height difference. So now h2 minus h1 is equal to hd. Now put the value of the equation number 1 and 2 in this equation. So h1 we already calculated d tan alpha 1, and h2 we calculated b plus d tan alpha 2. So here b plus d tan alpha 2 put at here. Now hd is equal to d tan alpha 1 minus b tan alpha 2 minus d tan alpha 2. Now d value we take a common, so right here d tan alpha 1 minus tan alpha 2 minus b tan alpha 2. Clear? So hd plus b tan alpha 2, right here b at here nearer to hd plus b tan alpha 2. So d tan alpha 1 minus tan alpha 2. So this equation is generally used to find out the horizontal distance between the instrument station to any object. So d is equal to hd b plus tan alpha 2 divided by tan alpha 1 minus tan alpha 2. So this one is a final equation, equation number 3 for finding out the horizontal distance. Now substitute the value of the d in equation number 1. So here we will put the value of d in at here. So in equation number 1, so we find out the h1 value. So h1 is a hd plus b tan alpha 2 tan alpha 1 divided by tan alpha 2 minus tan alpha tan alpha 1 minus tan alpha 2. So these are the equation number 4 for finding out the height of h1. Similarly, if we required height of the h2, so put the value of the d in a h2 equation, equation number 2 at here. Now we start a case number 2. Case number 2 is the height of the instrument axis near the object is at a higher position, means here object is there and instrument set up at a near the object is a higher as compared to another instrument. So here this imaginary line to top of the any object is a h1, and this second instrument imaginary line instrument axis to top of the any object distance is a h2, and from the instrument station first to any object distance is a capital D, and between the two instrument station distance is a small b, and at here batch mark is there, and instrument axis difference this one and this one is a hd. hd is a instrument axis difference. Now let's we start with take a one by one triangle. So for a first instrument setup, so we take a triangle PA dash P dash. Clear? We take a this triangle PA dash P dash and angle is a alpha 1. Clear? So we apply the triangulation formula. Tan alpha 1 is equal to h1 divided by d. So h1 at here and d is the distance between this point. So h1 is equal to d tan alpha 1. So this one is the equation number 1. Now we take another triangle, triangle number 2 PB dash P double dash. So this triangle is a PB dash P double dash. Now apply the triangulation formula like tan alpha 2. So tan alpha 2 is equal to h2 divided by b plus d. So this value. So h2 we take a h2 is equal to b plus d tan alpha 2. So this one is the equation number 2. Now hd is what is hd? So hd is a height difference h1 h2 minus h1. So hd is equal to b plus d tan alpha 2 we are already calculated here, okay, and h1 d tan alpha 1 we are calculated in a last slide at here. Now put the equation 1 and 2 at hd. Now b tan alpha 2 d tan alpha 2 and minus d tan alpha 1. Now we take a common, d value is a common, so tan alpha 2 minus tan alpha 1 plus b tan alpha 2. So hd minus b tan alpha 2 is equal to d tan alpha 2 minus tan alpha 1. Now we common the d, so d is equal to hd minus b tan alpha 2 divided by tan alpha 2 minus tan alpha 1. Now this d value shows the horizontal distance between the instrument station to any station point or any object. So now if we require the height h1 and h2, one by one we put the value of the d in equation number 1 and 2, means at here, clear. So if we require the h1, so h1 is equal to d tan alpha 1. So now here d value is already calculated, so put the value of the d in a h1 for finding out the h1. So we got the hd minus b tan alpha 2 tan alpha 1 divided by tan alpha 2 minus tan alpha 1. So this one is a final equation, equation number 4. Now this one is a typical case. In a case number 3, base of object inaccessible, instrument station are not at the same vertical plane as a elevated object. So here instrument station at a one at here and another at a some of the distance, not in a same line but and also not in a same level, clear, and object is put at a here. Now from the instrument station A, we bisect the angle, we bisect the top of the point P, and imaginary line is this. So from the imaginary line, top of the distance is h1, similarly h2. So here instrument set up at a B point, and this one is a horizontal line of sight, and this one is a horizontal line of sight to top of the any object distance is a h2. Now how to work on this method. So first of all, select two instrument station A and B on a level ground and measure B as a horizontal distance between the two stations. So here this value B, so from instrument 1 to instrument 2, distance is measured by the measuring tap or chain, and set up the instrument at A and level it and set up the vertical vernier 0 0 and bring the altitude bubble at the center and make the backside on a staff kept at a benchmark. So here benchmark staff is fixed, and we find out the height of the instrument. Now measure the angle of elevation alpha 1, so this one alpha 1, and measure the horizontal angle, this one BAC, this horizontal angle. So this one is also one of the triangle, so BAC angle theta is measured, and shift the instrument at a B point, and then after measure the angle, vertical angle alpha 2 from the top of the any object, and also measure the angle alpha, this one, as a CBA. So this one angle, clear. So alpha 1 is the angle of elevation from A to P, and alpha 1 is the angle of elevation of A to P, and alpha 2 is the angle of elevation of B to P, and horizontal angle BAC is theta, and horizontal angle CBA is alpha, and H1 and H2 we are already discussed, P1 P1 and P2. So from the instrument axis to top of the any object, and triangle ABC. So this triangle ABC, angle BAC is the angle theta, and ABC or CBA is the angle alpha. So as per the triangulation rule, ABC triangle summation is a 180. So 180 minus theta minus alpha. So these are the angle of angle C. Now AB line value is measured with respect to value is measured by using the measuring tab. So its value is B. Now we know the three triangle, one side of the triangle. Now there are using the sine rule. So for finding out the distance of AC, so as per the sine rule BC, so this BC distance, BC divided by B sine theta, BC divided by B sine theta, and divided by sine 180 minus theta plus alpha, and AC, this value, this one formula is a sine rule. Clear? So B sine alpha divided by sine 180 minus theta plus alpha. So now H1 is a AC tan alpha 1, AC tan alpha 1, and H2 is a BC tan alpha 1, BC, and this one is a H2. So H2 is a BC tan alpha 1. So we are already discussed H1 and H2 how to find. So only simply apply the triangulation rule, like tan alpha and tan alpha 1 and tan alpha 2. Now value of the AC and BC obtained from the equation 1 and 2, and RL of the P point is the height of the instrument axis, this one, plus H1. Clear? Or as per the instrument station B, height of the instrument axis plus H2 is the RL of P point. Now height of the instrument axis at A is the RL of benchmark, like benchmark at here. So benchmark plus BS, so is the height of the instrument axis at A point, similarly B point. Now in a next lecture we start examples, and this type of the example asked in a GTU in a 7 marks. So compulsory example is asked. So in a next lecture we start a example. Here we stop the lecture. Thank you.